In week 1, we learned about the assignment operator, this equal sign that stores data in a variable, where we say variable equals some sort of value. We're going to expand on that in week 3 to talk about all the different things that we can store in a variable. So first things first, MATLAB stores everything as an array, where an array is just a collection of data values that's organized in rows and columns and has a single name. So it's still variable equals value, but now it's values, it's plural, or it can be plural, where we have rows here, so let's say there's m rows, and then columns here, which is n columns, so a matrix. So that's how every single piece of data, numerical data at least, is stored in MATLAB. And we identify the size of the variable, the size of the data that it stores, by R times C, so rows times columns. Remember that, that's important. And there's different names for these specific variables. A scalar is a single value, it's a 1 by 1. A row vector has one row and any number of columns, so it's this direction. A column vector has however many rows and one column, so that direction. And then a matrix is more than one in either direction. And we don't need to define what the variable stores. It's just defined by whatever data we store there. So var equals whatever data. Okay, so how do we create these variables in MATLAB? First things first, brackets. Brackets are used to create an array. So as you're doing your math, you might think, oh, I can use brackets to group together things for order of operations. Brackets are exclusively used for creating arrays. They're creating arrays. So parentheses are used for order of operations. Brackets are used for creating arrays. Okay, so first things first, if we want to create a row vector, let's say I want to create an array that stores a bunch of ages, and I want to group together, I don't know, some ages of students. Let's say 6 students, and those are their ages, 18, 19, 18, 20, 21, 25. I can store them in a row vector, where I literally just type the numbers explicitly. I can separate them by spaces or commas. So if I do that over here, I can just do 18, 19, 18, 20, 21, 25. If I run this code, we can see it prints out in the command window, just like I typed it, as a row of values. There's no semicolon here, so it prints out, and here's what it looks like in the workspace. So we can see the name of the variable. Now it stores more than one piece of information, and it's a 1 by 6. It has 1 row and 6 columns. If we have data that we want to store that follows a pattern such as all the even numbers, where I have 2, 4, 6, 8, etc., all the way until I want to stop. Then I can use 2 different methods in order to create a row vector that contains a pattern. So linearly or evenly spaced a vector creates that pattern. The first one is the colon operator. To do this, I need a starting value, an increment value, and an ending value. So let's say I want to do all my even numbers. I would start at 2, and let's say we end at 20, and then my increment would be 2. This is the number to add to get to the next number. Yeah. So for example, if I have even numbers, I would have 2, spacing of 2, all the way until 20. So there we go. So here's my even numbers, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And we can see in my workspace, I see my values, and it has 1 row and 10 columns. Similarly, we have the linspace function. Linspace function also is used to create a linearly evenly spaced vector. So when I have that pattern, I just need slightly different information to use linspace. Note it's a function, so I'm going to use the name of my function, and then open close parentheses. And what does it need in order to call my function? A starting number, which for this would be, say I'm creating this vector over here. I would start at 2, I would end at 20, and then the number of values, I can see my size is 10. Okay, and where do I store my result? In a variable. So even 2 equals linspace, the name of my function that I'm calling, starting at 2, ending at 20, and give me 10 values. So there we go. It creates the same vector. So whenever we have a pattern, we can use one of two options, the colon operator or linspace. It just depends on what information you need. Colon operator needs a starting value, an increment value, and an ending value in that order. Linspace needs a starting value, stopping value, and number of points that you want to have in your vector. Okay, so that's a row vector. Ones where we have one row and as many columns as we want. A column vector is creating something where we have one column and any number of rows. So if we want to create that ages vector, that's a column, and let's say we want the same ages but stacked on top of each other, 18, 19, 18, 20, 21, 25. What we're going to do is we're going to separate them by semicolons. So for the row vector, they're separated by spaces or commas. We just literally just type them next to each other. For a column vector, they're separated by semicolons. So now I need to explicitly type a semicolon after each number. So ages 2, it would be 18 semicolon, 19 semicolon, 18 semicolon, 20, 26 semicolon, 21, 25. And we can see it prints out as a column in my workspace. And in my command window and in my workspace, I can see it's now the same values, but my size is now 6 rows, 1 column. So it's a column vector. The second way we can create a column vector is by taking a row vector and transposing it. So turning it into a column, essentially flipping it up on its end. And the way we do that is with the transpose operator. So there's two options. You can use the transpose function. So here's my function. But the more common way you do is by using the transpose operator, which is the parenthesis. So if I want to take my even numbers, 3, and I want to make them into a column, I can just transpose it. So there we go. Here, this little apostrophe takes my row and flips it on its end, flips it up, and turns it into a column. Okay, so here we can see, here's my numbers. They're now in a column. Same thing in my workspace. Okay, so that's a row vector and a column vector. A matrix is just a bunch of rows stacked on top of each other or a bunch of columns put next to each other. Okay, so I can create a matrix. Let's say, once again, I want my ages, but now I want to store them in a matrix for some odd reason. So let's say my first row is 18, 19, 18. My second row is 20, 21, 25. There's a couple things I can do. The most common way is to create each row and stack it on top of each other. So use the semicolon. So here, I'm going to stack my rows on top of each other. Or I can create my columns and put them next to each other. So put a semicolon at the end of these and put them next to each other. So if we look at those two, ages, I don't know, what do we have? 3. I can say 18, 19, 18, stacked on top of 20, 21, 25. And there we go. In fact, if we do this, we don't even need these brackets here. Same thing. Or we can create our columns, 18 stacked on top of 20, place next to 19 stacked on top of 21, place next to 18 stacked on top of 25. Here we go, same thing. If we do this, we definitely need the brackets around the columns. That's just the way it works out. This one is much more common. As you can see, it's less typing. But those are the different ways we create a matrix. We create our rows and stack them on top of each other, create our columns, or paste them next to each other. In the process of doing this, stacking rows on top of each other or putting columns next to each other, the word for that is actually concatenation, where we can create a matrix by combining pre-existing vectors or other matrices. So we can stack other matrices on top of each other, where commas and spaces are used to put things next to each other, and semicolons are used to stack things on top of each other. So these are the key things to remember when we're creating our matrices, when we're creating our vectors, when we're storing data in a variable. One other thing to note, make sure when you do stack things on top of each other, they have the same number of columns. And when you do put things next to each other, they have the same number of rows. Otherwise, it will not work. So for example, if I have an array that I want to put these this 3 by 2 next to a 2 by 2, I can't, because they don't match up here. There's nothing here. And MATLAB will not create something there either. It will not fill it with zeros. It's just like, no, these don't match up. You cannot put them next to each other because they don't have the same number of rows. Similarly, if I try to stack a 2 by 2 on top of a 2 by 3, they're missing a column here. There's not the same number of columns. So it will barf at you. It will not just fill in the space. It just says, hey, cannot do that. Okay. Last thing to note is the transpose, like I talked about up here, turns the row vector into a column vector. Same thing is true for a matrix. If you transpose a matrix, it just turns all of the rows into columns. So row 1 would become column 1, row 2 would become column 2, row 3 would become column 3. So if I try to transpose ages 5 equals ages 3 transposed, there we go. So here my first row becomes my first column. My second row becomes my second column. So that's another way that we can modify and create matrices and arrays, is transposing. Okay, so we can create vectors, we can create matrices, we can create scalars, and we can see how they look in the workspace. That's great. There are some other ways we can create matrices. These are the most common ones over here, but a lot of times we'll see these functions used in order to create matrices, zeros, ones, and I. They all work very similarly. If I do help zeros, zeros creates a zeros array, so it creates a matrix filled with zeros. Here's the couple ways to use it. So if we give it a single number, if I just say zeros 3, it'll create a 3 by 3, 3 rows, 3 columns of zeros. Or I can give it this number of rows, so 2 rows, 4 columns. It'll create a 2 by 4, so 2 rows, 4 columns. So zeros is really useful, creating an array full of zeros. Ones creates a matrix full of ones. Zeros, ones, and I creates a matrix of zeros with ones on the main diagonal. So they all work the same. If you give it one single number, it'll create a square matrix, same rows, same columns. If you give it 2 numbers, it'll create that many rows and that many columns. So here's what I looks like. So ones along the main diagonal. And we'll see that a lot when we get to linear algebra. Rand I, you'll see that in class. You'll see me use it sometimes, just create a random matrix. So you might not necessarily use it, but I want you to be aware that it exists. It creates a matrix of random integers, provided the number of rows and number of columns. These functions up here are functions that are commonly used in conjunction with arrays to determine information about the array. The size function, help size, looks like this. There's lots of ways to use size. We will go over all of these in class. But if I just say size of A, or I guess size of ages 5, it gives me a 1 by 2, where it gives me the number of rows that ages 5 has and the number of columns that ages 5 has. There are other ways to use it, but that's the main way. This will get you pretty far. There's examples down here as well, but we can see the size function is used to determine how many rows and how many columns that an array has. The length function is similar to size, but it returns the larger of the two numbers. So the length of ages 5 is going to be 3. So size is typically used with arrays or matrices, and length is typically used with vectors. Okay, but you can get the information with size. You can get the same information with size for either one. Numal returns the number of elements in the array. This is useful. It tells you how many values you have. So for a 3 by 3, it'll give me, it's got 9 values. Endims it can be useful. It's not terribly useful though, but it is in there just to be complete. Okay. So we can create arrays. filled with zeros, filled with ones, filled with identity, or with ones along the main diagonal. We can figure out size of our arrays. We can create arrays with numbers that we have. We can create linearly spaced arrays. There's lots of ways that we can create an array. The second part of week 3 is modifying those arrays. So using something called indexing. It's the act of accessing individual elements of an array or subarray by identifying which locations to use. So locations start at 1 and increment by integers. So location 1, 2, 3, 4. If I go up to some of my vectors here, this is in location 1, location 2, location 3, 4, 5, 6, 7, etc. And we can modify and change and use each of these individual locations one at a time or as a group. That's what indexing is identifying which elements or subgroup of elements to use or modify within a single array. Okay, vectors can be indexed with a single number, because if you talk about location 1, there's only one location. Where here's the name of our vector, or the name of our variable. And this identifies which part of it to use. And here's our syntax. Name of vector, or name of variable, open close parentheses, which part to use. Think about it as a function call. You're calling to say which functions, which locations you want to use. So if I look at ages, just ages, and I say location 1, it gives me the first value in ages. That's all of my values, but I don't want all of my values. Let's say I want the 4th value. I can say the 4th value. Same thing with a column. Doesn't matter. Just it'll grab whatever location you want. And you can do more than one location. So location 1, 3, and 5. It'll give me location 1, 3, and 5. With matrices, it's very similar, but with matrices, we need 2 numbers. We need the number, whatever rows we want to access, and the number of columns. So it's row column indexing. So same idea. Here's the name of your variable. And here's where you identify which locations or which part of it you want to use. So for ages 5, that's what it looked like. So for ages 5, I can say, okay, give me row 2, column 2. And it gave me the 21, the element in row 2, column 2. Or I can say, give me the elements in row 2, columns 1 and 3. Ooh. Oh, my bad. Columns 1, or row 1 and 3, column 2. There we go. So grab the 20 and the 25. So I can use a matrix in either location as well. We can also index matrices using a single number. It's called linear indexing. It's not used very often, so I'm not really going to focus on this. Just note that for linear indexing for a single matrix, this is location 1, 2, 3, 4, goes down, and then this would be 5, 6, 7, 8, and then etc. And it goes all the way until the end. That's linear indexing. It's not used that often, but it is possible. Okay, so that's the basics of indexing. It's the basics of saying, okay, I don't want to use this entire matrix. I want to use part of it, and then we identify which part. Indexing is used a lot, so there's some shortcuts when it comes to indexing. The first thing is the end keyword. The end keyword automatically refers to the last element in the index. So it's valid when we have whatever variable, followed by open close parentheses, and then the end refers to the last element in the vector, or the last element in the row, the last element in the column. The end keyword is valid only when indexing. Okay, if it's not inside of these parentheses next to a variable, then it means something else. It means something else. Okay, we'll talk about more about what it means in a couple weeks, but we've seen it already with the function. We have a function file that has an end. Okay, but if we have end within the variable and parentheses, it means it's talking about the last element, the last row, the last column, the last element in the array. So I can replace the 3 here with end. Same thing. The second shortcut, the colon operator. The colon operator is super useful. It's used to refer to all locations in the array. Okay, we've already seen the colon being used when we created some arrays. Let me close out of this. This one here, we've already seen the colon operator being used here to create an array, and that is completely valid. Okay, completely valid. We will use this all the time. However, when we're talking about indexing, the colon can also be used to refer to all locations in an array. So here, this is when the colon is next to a variable, followed by open close parentheses, and here it means all. So here's all the rows, followed by whatever columns we want to index. Same thing, all the rows, followed by more than one column that we want to index. Here it means all the columns and however many rows. So if I want to look at, go back to my ages, all the rows in column 1, that's what it looks like. Or I can say, no, wrong one, ages 5, here we go. All the rows in column 1, there we go. Or I can say, in column 3, all the rows. So I can use it to indicate all. So that's our second shortcut. Okay, really useful. So that's indexing. Now we want to put it together. We can create an array by saying var equals whatever values. Here I created an empty array. And we can access or index the individual elements or sub-elements in that array. Okay. Now we want to go ahead and put it together by modifying. So back to the assignment operator. There's two sides to the assignment operator. There's a left-hand side where it talks about what variable we want to store things in. And on the right-hand side, we have what to store there. Now, instead of just the variable, the whole variable being created, now we can say, okay, the variable, and now which parts? Which parts? If we want to modify the whole variable, if we want to create a whole variable, we just say var equals all the values. Insert all the values. Our MATLAB will obviously barf at me. Insert all the values. However, we can modify that and say, okay, which values? Which locations? So here's our syntax. Variable, which locations do we want to modify and what do we want to store there? So that's what it comes down to. So here we have our indexing on this side where we're saying, okay, here's my variable, and we say which parts of it. Is it a vector? Is it a matrix? Which rows, which columns, or which values? And then here we can store whatever we want. Just note the number and size of what we're changing on the left needs to match the number of values we have on the right. Okay, so we can't say, okay, I want to change these values in this 2x3 orientation, and I want to put these values in there. It doesn't match. It's a one-to-one correspondence. There's not enough numbers to store in the left-hand side that I gave it on the right-hand side. Note it needs to match the number and size, so it's the same number and the same orientation. The only caveat of this, if it's a single number, so if I just assign it all to like 10, it will copy 10 into each location. But otherwise, we need to have the same number and size. Okay, and we will look at extensive examples. Two more things to comment on. New locations can be created by assigning to desired locations. So we can say, okay, variable in these locations equals values. These locations do not have to exist. They can be outside. So I technically could say ages 5 ages 5, row 4, comma 6, which doesn't exist, and set it equal to 10. It does do that. It's not a very good practice, but you can do that. Notice anything that didn't exist before was made to be zeros. Not good practice, so minimize the amount of times and how you do that. Lastly, we can delete elements by assigning things to empty. So if I want to delete ages 5, which rows? Let's say rows, all the rows in columns 3, 3, 4, 5, 6. I can just delete them by setting them equal to empty, and that's how you delete them. Okay, so we will do lots of examples of creating variables, modifying variables, lots of things to go over, lots of things we can do with this. I'll see you guys in lecture.